Alright, hell yeah. So we have dynamics, and we got a really hard problem. So we got motion, we have a thing spinning, and we have a pivot point that's not in the center of the circle. So we call this thing having eccentricity. So there's one rotation. And as this thing rotates, this actuator, called a follower, goes down and then up. And so the first thing that I would do for some of these problems would be like, well, okay, the actuator is going to be that high, and then it's going to come all the way down to here. You know what I mean? At least just get an idea of what the motion is. Okay, but now let's go to the problem. It says we want to find the speed of this actuator when this angle is 60. And so let's put this back on. And so this is just some representative angle. When this is 0, the angle is on the horizontal. So this is going to be 0 angle. The actuator would be up there on that green tape. Now at 60, so I do have these marked at 45, 60, and 75. So right there is a 60-degree angle. And so what I'm going to do with this problem is use the 3-point method. And for this, you don't even need 3 points. We're just trying to find velocity, but usually 3 points because you're going to get the velocity before, the velocity after, and you can use those two velocities to find acceleration. All right, hell yeah. So I just marked out 45 degrees, again 60 and 75, and then marked those locations where the actuator would be. Then I came in and I measured those distances. So this first one is 17.5, the second one is 18.2. But if we're just getting velocity, you know what I mean, we're not doing anything fancy, we're just saying, hey, it's basically traveling 17.8, 17.9 millimeters in the time it took this to spin from there to there. And so the cool thing about this is that this thing is spinning at a constant speed. You know, maybe it's hooked up to an electric motor. Electric motors are perfect for just having a constant speed, as long as torque and all things considered are relatively the same. You're not having big changes in torque. Okay, so then we kind of come in here to do the actual problem. And this will give us, hopefully, a decent solution. And so we have... So we have this change, the actuator changed by 17.8. We need to know how fast this thing is spinning. So it says 1,000 revolutions per minute. Anytime you get revolutions per minute, I would definitely at least change to revolutions per second. And what you're going to find is you get to divide by 60. So it's 1,000 revolutions per minute, 1 minute, there's 60 seconds. Using factor label, you're going to divide these two numbers to get revolutions per second. So about 17 times a second. But every second, this thing's spinning 17 times, you know, so still, you know, is that going to be useful? I got it into degrees. I was just like, well, there's 360 degrees in one revolution. Revolutions cancel. So we're going 6,000 degrees a second. And what I swept out was little distances of 15 degrees, from 45 to 60, 60 to 75. So what I do is I take 15 degrees divided by 6,000 seconds. Degrees cancel. Seconds pops upstairs. This is going to be my change in time, 0.0025. So now, basically, the equation for velocity is change in position and what time it took to change that position. How long did it take to go from here to here? And we can see that took 0.0025 seconds. So, so we have this 17.85 divided by that 0.0025, and we get 7,140 millimeters a second. Use factor label again, or just divide by 1,000. We get 17.14 meters per second. Now, the bummer is I had to do this video over again, and just it's probably more concise. You know what I mean? But 10 minutes ago, I did not look up the answer in the back of the book to this problem. I already did, so let's pretend like we didn't. The answer's right there. But I was, because I was just like, I wanted to know, using this method, like how accurate are we? And we're 2.9% accurate, if you want to just look at that. But so 16.96. But yeah, it was a really cool moment, because I just had to do this video again, just because it was too bright. So we get the answer in the back of the book is 7.35 meters per second. And they also specify that it's actually traveling downward. I think with our example we could have saw that it's traveling downward. But hell yeah. So the answer is 7.35 meters per second. But the whole idea is to be like, hell yeah, we just set this up. Now this was kind of complicated. Hopefully I get some views on this. And but you could do something fairly simple and similar using protractors, you know, within the time you're going to scratch your head trying to solve a problem like this. You might as well just get a quick answer. So that's what we do. And hell yeah, we're within 2%, 3% error. So that's really cool to see. Okay, so this was part 1. Part 2 is we gonna go over kind of a longer video, but we go over, hey, what is this actuator doing? You know what I mean? Does it stop at the top? Does it stop at the bottom? What's its velocity? And then what do we know about its acceleration? So we're gonna take a look at that. All right, hell yeah.